Hello and welcome to the first theory prep video. Today we'll be talking about what is a proof. So I'll give a quick example proof and then we will talk about how to do your first type of proof, your first proof technique, universal statements. Great, let's start with an example. So we're going to prove that the sum of two even numbers is even. And the first question you might have is, well, I already know this fact to be true. It's pretty common, so why do we have to prove it? I have two answers, they're sort of similar. The first one is that it's a little bit like lifting weights. Often we're going to prove things in this course that you might already know are true or you might have already seen. But the important part is not the fact that we're proving. The important part is the actual proof itself. And so having experience with those proofs is going to make you better at these proof techniques, and then you can tackle the harder problems. The second is that often doing a simple proof that we have a lot of intuition and familiarity with helps you understand it better. And so after we do this proof, we'll generalize to a technique called proof of universal statement. And so you can understand it in the simpler case before we give the general proof technique. So let's try this. And the first thing you should do whenever you see a theorem is make sure you understand it. In this case, you probably understand what it means to add two even numbers together. But if you didn't, you could write some examples out. 2 plus 4 equals 6. We could do negative numbers as well, right? Negative 4 plus 4 equals 0. Well, in both these cases, two even numbers, we get an even sum. And the issue is that we don't quite have a definition of even numbers. So it's hard to say how are we supposed to reason about what would happen if we add them together. So let's get a definition. Our first definition might be that we say a number n is even if there exists another number m such that n equals 2m. And whenever you see a definition, always think to yourself, well, does this definition make sense? In this case, we already have an idea intuitively of what an even number should be, so we should check to make sure the definition corresponds exactly to what our intuition is. So for me, a number is even if you divide it by 2 and you get another number. So n is even if n divided by 2 is some other number m. And this is exactly what we're saying here, because you can just multiply both sides by 2 and you get n equals 2m. These are equivalent statements. One is true exactly when the other one is true. And so this seems like a good definition, If like 2 is even, yep, there exists another number, like 1, that multiplied by 2 gives us 2. Even works for 0, 0 is even, and 0 equals 2 times 0. But we have a small issue here, because what exactly is a number? And this is an important lesson. In math, it's really important to be precise about what we mean. A number, well, 2.5 is a number, right? It's not a whole number, but if 2.5 is a number, then by this definition, 5 is even, because 5 equals 2 times 2.5. And that seems not ideal for us. So that means that we have to refine our definition a little bit. So what do we mean? We want m to be what we call an integer. And the integers are you might have heard the term whole numbers before, so 0, 1, 2, etc., all the way to infinity. And they also extend to the negative integers, -1, -2, all the way down. So if we define this entire set, that will give us the integers. And since we use the integers so much, we have a shorthand for them, which is this, what we call blackboard Z, but it's a Z with an extra line through it. And this is our first example of a set, which is a collection of unique elements. And so what we want is for m to be in the set Z, right? That's what it means for m to be an integer. It means it's one of these numbers, right? So we use this little arrow to indicate that m is in the set Z. So really what we want is, in order for a number to be even, so some number n is even if n is equal to 2m for an integer, for m in Z. And we're going to write a little bit of a refined definition and get exactly that. So an even number is an integer n such that n equals 2m, where m is an integer. And now this is a much better definition, right? Because now 5 is not even by this definition, because 5 equals 2 times 2.5, right? The only quantity that you can multiply by 2 to get 5 is 2.5, and that's not an integer. So Now our definition is sufficient and captures the intuition that we want it to capture. We still have to do our proof. So we want to show that the sum of two even numbers is even. So let's say we have our first even number n, and then we have our second even number n prime. And by the definition, since they're even, we know we can write n as equal to 2 times m, where m is an integer, right? That's exactly what our definition says. And again, by our definition, we know that we can write n prime as 2 times m prime, where m prime is also an integer. So that's, again, by our definition, right? That's what it means for a number to be even. We can write it as 2 times another integer. So now we want to look at the sum, right, of these two numbers. So n plus n prime, by substitution, right, we just replace n with 2m, because those are the same thing. And we replace n prime with 2m prime, and that'll give us 2 times m plus m prime. And we know m plus m prime is an integer because m and m prime are both integers. When you add two integers together, if you add two whole numbers together, you get a whole number. So that shows that we can write n plus n prime. We can write the sum as 2 times an integer, right? We can say m plus m prime is in the integers. And so that means, again, by our definition, that the sum is even. So that completes the proof. Great. So now let's take a step back and talk about what is a proof at a high level. And then we'll take this example that we just did and show how each of those parts fit together, because often having an example is really helpful with a definition. Let's now go over what a proof is. A mathematical proof of a proposition is a series of logical deductions from axioms leading to that proposition, thereby establishing it as true. So in order to really understand this, we sort of have to understand what is a proposition and what is an axiom. A proposition is a mathematical statement that's either true or false. So we can have simple propositions like 3 plus 4 equals 7. That would be a true proposition. Or 3 plus 4 equals 10. That would be a false proposition. Or we could have slightly more complicated propositions. To give an example of that, a proposition is there does not exist, and we use this backwards E symbol to indicate there exists. But if we cross it out, that's shorthand for there does not exist. A, B, C, and D. Remember, this symbol means in the set, as we just covered, of usually if we put a plus on top of a set, it means only the positives. So there do not exist positive integers such that a to the fourth plus b to the fourth plus c to the fourth equals d to the fourth. So overall, the proposition says there don't exist four positive integers such that a to the fourth plus b to the fourth plus c to the fourth equal d to the fourth. And this is actually proven false by Professor Noam Elkies when he found four numbers that this is true for. So there's lots of different things that can be propositions, but the important thing is that they're either true or false. So importantly, if we got rid of this first part here, then the proposition, this is no longer a proposition, because a to the fourth plus b to the fourth plus c to the fourth equals d to the fourth. Well, that's true if their numbers are all 0, but it's false if the numbers are all 1. So it's no longer a proposition because it's no longer either true or false, right? It's sometimes true and sometimes false. So propositions need to be well defined as something that we can prove or disprove. Now, let's talk about what an axiom is. Kind of at a high level, axiom are propositions that we assume is true. So to give an example of this that you might have seen in high school in Euclidean geometry, you could originally assume 5 axioms, like 5 things that were true about geometry. For example, like if you have 2 points, you can connect them by a straight line segment. And actually, in other forms of geometry, like spherical geometry, not all of the axioms that Euclid assumed will hold. And that's perfectly fine, because what we're doing in math is we make up some axioms, right? Things that we're going to take as true, and then we just build up from there. And in particular, mathematicians use axioms, usually a set of axioms called ZFC, which are really, really basic assumptions. As an analogy, you could think of it as coding by using punch cards. But in our classes in 121 and 124, in this class, in CS50, they don't make you use punch cards to program. You can use Python or even C, which is still levels and levels of abstraction above. And in a similar way, we're not going to make you prove stuff from ZFC. we're going to let you basically use anything from high school math as prerequisites. The one important caveat is, for example, in the proof we did today, if your knowledge trivializes a proof, then you shouldn't use those facts as axioms. So let's summarize. So what is a proof now that we know what a proposition and an axiom is? A proof is a logical argument based on things that we know, right? That's what an axiom is, to demonstrate that a new proposition we are considering is either certainly true or certainly false. So hopefully that demystifies a proof a little bit. It's a logical chain of arguments from things that we know to some result that we want to prove. And so let's apply this definition of what is a proof to the proof that we just did. Remember, we begin by stating a proposition. The sum of two even numbers is even. That's a fact. It could be true. It could be false. And so that makes it a proposition. And then what we do is we fix arbitrary even numbers. We can write that as 2m and 2m prime, because by definition, an even number is 2 times some integer. And then we wrote out their sum, right? And we used the fact that addition distributes over multiplication to rewrite it as 2 times, in parentheses, m plus m prime. So that's sort of using an axiom there, right? Because it's using something that we know to be true, that addition distributes over multiplication. And then we use another axiom, which is that we want to show that this was an even number. So we want to show that the parenthesized expression was an integer. And we know that when we add two integers, we get an integer. That's because, right, addition is closed over the integers. It's sort of fancy mathematical way of saying if you add two integers, you get an integer. But all of that is just things, propositions we're assuming as true, right? They're like axioms, knowledge we already know from high school math. So you can see exactly how this definition of a proof really plays out. We had something we want to prove in red, and we used facts that we knew in blue to construct an argument for why this must be true. Great. I claim now that we know how to prove a universal statement. We've gotten our first proof technique. And to see that, let's rewrite this theorem a little bit. Another way of saying that the sum of two even numbers is even is that for any two even numbers, n and n prime, n plus n prime is even. And we'll introduce a mathematical shorthand here, which is this upside down a, which means for all or for any. That way we can rewrite the theorem as for any n prime even, n plus n prime is even. And so now we can talk a little bit more about how to prove a universal statement. A universal statement is a statement of the form for any element z in some set S or subject to some constraints. There's we say blah 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 about z. We say something about z. Like z squared is a multiple of 5 or some random stuff like that, right? It could be any statement of the form for any of these objects. This thing is true, and let's outline how we proved it for the even numbers, and then that'll suggest a proof statement or a proof technique for all universal statements. So the first thing we did is we needed to prove that if we have two elements that are even, that their sum is even, right? But we can't assume anything about those elements except that they're even, because it has to work for all even numbers. You can't assume it's divisible by 4. You can't assume that's a power of 2. You can only assume that they're even, which is by definition to say that there's some integer when multiplied by 2 that gives that. And so the fact that we know nothing about these elements other than that they're even, in order to capture that fact, we use the term arbitrary even elements, right? So the first thing that we did was we fixed some n and n prime arbitrary even elements, right? And then the second thing that we did was prove the conclusion that n plus n prime is even, right? And so we can generalize this to all universal statements. It suggests that the first step is, since we have to prove it for all elements satisfying those constraints, is we should just fix some z in S, right? Some arbitrarily. And then second, we should prove that statement for z. And because we fixed it arbitrarily, then the only thing that we assumed was, it's part of S, it's even, it's an integer. That means it must hold for all of the elements that share that property, thus proving the theorem. So this is the first proof technique, which you guys will use a little bit on your homeworks. And let's do one more universal statement to help clarify here. Okay, now here's another theorem. For any n in z, remember we're using the for all notation again, so this means for all integers and m, where m is even, then their product nm is also even. So we'll follow the same strategy. First, fix arbitrary n in z, right? So fix an arbitrary integer and m even. So that means that we know that m is equal to 2m prime for some m in the integers, right? Because that's the definition. This is by definition. So that means that their product, nm, and now this is step 2 where we're trying to prove the conclusion, equals n times 2 times n prime by substitution. And that's just 2 times n m prime. And these are both integers, so their product is also an integer, right? Again, this is just using high school facts that we know. When you multiply 2 integers together, you get another integer. And that means that their product is of the form 2 times some integer, which means their product is even. So now we've successfully completed the proof. So again, we use the universal statement proof technique again. You fix arbitrary elements that satisfy the hypotheses that, like they have to be an integer, they have to be even, they have to be power of 3, and then you prove that the results, the conclusion must hold. Great. So that's most of the content for this video, but I want to address one question because I think it's sort of a nagging question when you start to do proofs, which is like, why do we need to prove these things? Like, why can't we just try some examples and, if you try enough examples, that's probably right? So like, you just try adding some even numbers, try adding some large ones, some small ones, some like negative ones, you add 0 in there somewhere, and then the statement is probably true. Well, the reason is that's not a proof, right? If you try it for a certain number of numbers, like you try it for some group of even numbers, then you know that statement is true for those even numbers, but you don't know that it's true for anything else. And here's a good example of this. So let's say our proposition is for any n in the natural numbers, and so let's define the natural numbers. The natural numbers is equal to all the integers that are non-negative, so 0, 1, 2, ... Sometimes people define the natural numbers as without 0, but we'll define it with 0. And so we're saying for any natural number, this quantity, n squared plus n plus 41, is prime. And if we just try stuff, it kind of looks like that's true. If you try 0, you get 41, that's prime. Try 1, you get 43, that's prime. You keep trying numbers like 2 all the way down to 39, and it's still prime. It's going to be prime for all of these numbers. 39 plus 39 squared plus 41 is 1601, which you could just take my word for it. It's prime, or you can look it up. But so we might just give up. We're like, we tried it for a lot of numbers. It's probably true, but it's actually not true. If you take 40 and you add it to 40 squared, and then you add 41, you get 41 squared, which is clearly not prime, right? Because it's 41 times 41. So this theorem, this proposition is actually not true. It's false. But you can't, it serves to give an example of why you can't just try things and conclude from that. So this is why proofs are necessary, because we have to be able to, when we reason about a universal statement proof, right, we're fixing arbitrary values. We're just fixing some integer, some even number. And so it must hold for all even numbers and all integers. Whereas if you just try things, you can't always get all the cases.